All right, everybody, welcome to this session. And our first speaker today is Jessica Gadling, and she's going to talk to us about embracing GraphQL. Thank you.
Hey, everybody. All right, mic's working. Hi, I'm Jessica Gadling. I work for the Chan Zuckerberg Initiative. I'm a staff software engineer, and I'm learning how to use this clicker. All right, so I work for CZI's Science and Technology Division. Our science division has a mission to make it possible for scientists to prevent, cure, or manage all diseases by the end of the century. No big deal, small ambition. And our SciTech organization helps build software and services to advance that goal. All right, this talk is mostly going to be about GraphQL, but we can't really talk about GraphQL without talking about REST, which is its main competition in the web services space. So what is REST? It's an architectural pattern. It's important to know that it's not a protocol. It's basically a pattern for mapping HTTP's interface. So that's HTTP's methods, response codes, and routes into a way to exchange data between a client and server. REST has been around a long time. It's been kind of widely used and the de facto standard for web service APIs since roughly around 2007, 2008. And it replaced a really complicated XML-based messaging protocol called SOAP. This was a long time ago. We don't have to get into what SOAP was. So let's get into kind of the anatomy of a REST request. This is curl, a pretty popular command line HTTP client. And so if we wanted to curl a REST API, all we need to know is the URL for the resources that we want to query, maybe supply some optional or even required query string parameters. And what we see here is if we just know the URL, we can get a bunch of data, and the server is completely in charge of the response that we receive. All right, I don't want to throw any shade on REST. REST is actually really great. It's been the gold standard for a long time for a lot of really good reasons. Basically, it's simple to build clients and servers because both HTTP client libraries and JSON serializers and deserializers are ubiquitous. They exist in pretty much every programming language you can think of, and they're nice libraries built on top of some basic primitives here. Reasonable defaults here mean that clients only need to know which URL to fetch, and they get a bunch of data back. So you can actually get started using REST APIs without reading the docs in any particular depth. You can kind of query them, see the response, and then go from there. There's a bunch of industry standard tools like caches, authorization proxies, and load balancers that work really well with HTTP. So with REST, we can reuse all of this infrastructure to build our APIs. REST has been around a long time. Odds are someone on your organization has worked with it before. They can show you how to use it. There's a lot of documentation on the internet to help you out. So it's basically really easy to get up and running really quickly. Here's a small snippet of the API documentation for an API that I worked on not too long ago. This documentation scrolls and scrolls. We can see that we have a whole lot of endpoints for what was ultimately a pretty simple application. We had an application that managed genomic sequences and then built phylogenetic trees from those sequences. But we were building this API kind of organically. As our front end needed more functionality, we were adding more routes or more query string parameters to our existing routes. Every time we had to add a new feature, we were evaluating whether it made sense to modify an existing endpoint, figuring out whether or not we needed to change defaults and introduce some breaking behaviors, and decide whether or not to take on the maintenance burden of managing like a combinatorial explosion of parameters to our APIs or creating a whole bunch of additional APIs. So REST is great, but there are some pretty common pitfalls building REST APIs. We often wind up with route bloats, where we have a combinatorial explosion of get this by that. Most API interfaces have some sort of data relationships defined, and we wind up having to search data by some other data, or we can basically wind up in the same situation with parameter bloat, where we can support a bunch of different ad hoc filtering parameters, response shaping parameters, and so on. So these are all pretty common. So we also often start REST APIs really simply. We just build the functionality that we need when we need it. And it's not often that we have the opportunity to kind of look at what we've built holistically and see if our APIs would be better implemented with some kind of standard patterns and see if we can build them better from that point on. Sorry. REST has no particular opinions about the inputs and outputs of your API endpoints. The spec actually doesn't even say JSON. JSON is just the norm. So that basically means that our inputs and outputs are not typed by default. These days we have some standard tooling like Swagger specs, OpenAPI documentation, but these are not at all universally implemented, and even when they are implemented, we often don't have all of these types integrated with our client frameworks. So our clients are often left to kind of hand edit types that match whatever is returned by our API service. So this next one is really the big one for me. So we're building software in the science space. And data in the science space is almost always all about relationships, whether we're talking about the relationship between multiple structures in a cell, or whether we're talking about the relationships of one species to another. REST APIs don't really provide any standards here. There are a bunch of different guidances depending on which documents you read as to how to express relationships in data. But the fact that we don't have any standards and every API author has to do this discovery, implement their own relationship handling, means that we basically don't wind up with very good tools that help us express these relationships and query them and so on. And so since there's not a lot of standards for working with REST and REST inputs and outputs, there's even just our tools for managing basic non-related data are pretty limited. Like REST API clients don't do a lot for us. They basically issue HTTP requests and deserialize the response, and they rarely do more. All right, so GraphQL. GraphQL is a data query and manipulation language. Again, it's not a protocol, it's a query language. So it's a query language kind of the same way SQL is a query language. So it's meant to provide a way to access data from a data source. It was open sourced by Facebook in 2015, and it's had its own foundation to guide its progress since around 2018. There's the GraphQL Foundation. The reference client and server are in TypeScript, but don't let that scare you. There have been translations to basically every major programming language in use these days: Ruby, Python, Golang, so on and so forth. At the end of the day, we're typically still using HTTP as a transport. So we're exchanging JSON data over HTTP, but we care a lot less about HTTP routes and verbs and response codes when we're working with GraphQL. There's some additional functionality that most GraphQL clients and servers also expose. So GraphQL services can allow clients to subscribe to real-time data updates over WebSockets. I'm not going to get too much into this functionality today because I'm a little less familiar with it, but it is basically universally supported by GraphQL toolchains. All right, so GraphQL thinks of APIs in terms of a strongly typed graph, and it allows our clients to traverse the graph however they see fit. This is an example that I'm going to be using throughout the rest of the talk, so let's get a little bit familiar with it. We've got a sample collected from a source, let's say a human nasal swab, for example. We run that sample through a genomic sequencer, and we get output from that sequencer. And then based on the output from the sequencer, we can compute a consensus genome. We see that we have relationships between each of these entities. Basically, each entity points back to its source. And let's look at how this schema could be defined using GraphQL's schema definition language. These schema specs should be pretty familiar. If you've worked with any sort of strongly typed or object-oriented programming language, they're not going to be too shocking. So in GraphQL schema definition language, we have the ability to define an enum and set some possible values for that enum. We can create interfaces. So anything that implements this interface inherits this name field. And we can create types that implement interfaces. And we can define a bunch of fields for this type. We have a variety of scalar data types that GraphQL supports natively. So we've got strings, ints, floats, booleans, the usual, as well as the fact that GraphQL supports creating custom scalar types. So I'm not going to get too deep into all of the weeds of all of these custom scalar types, but you can use its built-in types pretty simply. Here we see that our sample has a sequencing reads field that's an array of sequencing reads. If you're used to Python, you know that there can be some sort of ordering issue when defining relationships between different types. Since GraphQL is graph native, it doesn't have these problems. It knows that it's going to be creating an interconnected graph. And we can define a sequencing read, which also has a reference to a sample. Any questions, comments? Okay. And we also got a field that refers to our enum. So this is our, yeah?
Oh, yes, we're not saying which ones are sort of forward and back references at this stage?
We don't specifically have to say which one is forward and backward at this stage. We're just defining types. And I mean, maybe we should name our fields a little bit better, and our sample field on sequencing read should be source sample or something, so we have a better name for that edge. But just kind of the fact that these relationships are one field to many rows or one field to one type kind of tells us a little bit about the nature of that relationship.
It's implementation, it's not right.
Yeah. So the previous slide was kind of showing what our user schema definition looks like, but all of that needs to get wired into our GraphQL roots. So GraphQL has two root types. It has a query type and a mutation type. If we're translating to REST, query type is kind of the equivalent of a REST GET request. So we fetch data without changing state on the server. And mutations are basically all types of writes are encapsulated by a mutation. So put, post, delete, you can have mutations that perform all of those actions. Basically, your docs and the names of these fields kind of imply what any given mutation will do. So we'll kind of copy over an abbreviated version of our schema from our previous example. And here we have our schema, which is the start of the data that we expose to our clients. So we see that we have a root query, we have a root mutation. And then when we define our root query, we can define the fields that are available from this root. So we have a sample that takes an ID parameter. This exclamation point next to ID means that this is a required parameter. You can't fetch a sample without an ID, and our API framework will explode and tell you you need to supply an ID if you try to fetch a sample without one. And this field returns a single sample. We have a samples field that returns a list of samples. In this kind of simple case, it doesn't accept any parameters, but it returns a list of samples. Sequencing reads, kind of same. We can return a list of sequencing reads. When you issue a query, you can query for any combination of fields. You can run one query that fetches a single sample and a list of samples, or just sequencing reads. You're not limited to just fetching one field. And for a mutation, we can have a create sample mutation that accepts a couple of parameters. In this case, these are a required name and collection location parameter, and a delete sample mutation. Is this pretty clear? Questions?
How can you make that you can only do either create sample or delete sample?
You can also execute multiple mutations in a single GraphQL request. So you can even create multiple samples in a single GraphQL request. So basically, GraphQL supports field aliasing, so we can query for multiple instances of these root fields really easily. Yeah, a single query, we can request multiple different samples by ID as well. We just need to give them an identifier so we know how to find the response for a given sample.
Presumably you get the same sort of control in terms of authorization for accessing these. At some point you can lock them down.
Yeah, at some point we need to lock these down. This is just the schema definition. So this is basically what we're exposing to our clients. All right, so an anatomy of a GraphQL request. This is a typical GraphQL request issued using curl. So we see here in particular that this v1 GraphQL path, this is the entry point to our entire graph. So we don't have different routes for different parts of our graph. Our GraphQL server is returning any data that you ask for over this one route. So we can see that our query here is a little bit more complicated than our REST query. We are explicitly asking for all of the fields that we want returned. And we see in this example, we're actually getting a top-level samples field as well as any sequencing reads available for those samples. So we're fetching data from multiple entities in one request. This allows us to have a lot of control over the response. We see that the response is shaped almost exactly the same way that our query is shaped. So we return samples and sequencing reads that belong to those samples. All right, so REST and GraphQL API authors need to associate some bit of functionality with some part of a request. So for REST APIs, we're associating typically a function with an HTTP route. And here's an example of some Flask code. I don't know if anyone's used Python Flask, but it's a pretty simple REST API service where we're associating an HTTP route with a unit of work, which is this myEndpointFunction function. So in GraphQL, however, all of our data is coming through a single route. We need a way to figure out how to do work when someone asks for a given piece of data. So in GraphQL, we are associating functions, and these functions are called resolvers. If you see the word resolvers, don't freak out, with a field in our schema. So Strawberry is a pretty popular GraphQL API server library for Python. And here's our root query type, and here's how we associate a function, so function that loads samples, with a field in our schema. These ideas are roughly equivalent. Really, the only major difference to keep in mind is that in REST, typically you're only calling one function per HTTP request. And in GraphQL, typically you're going to be running multiple resolvers to satisfy a single request, depending on what that request was structured. Basically, every GraphQL API library worth its salt includes a nice little GraphQL playground. It exposes a GUI that makes it easy to kind of navigate your type graph and compose queries with kind of point-and-click interface. If you've used Postman or any other type of HTTP client libraries with nice GUIs, they also support all this. Since our GraphQL schemas are fully introspectable, these tools can basically issue a query to fetch the entire schema and then build a reasonable UI based on that. I want to give a shout out to Relay. So I don't know if everybody here has used React or built front ends. I'm personally a back-end developer, so this is a little out of my wheelhouse, but React is kind of the de facto standard framework for building interactive web UIs. And it allows you to build these web UIs out of smaller reusable components. So you can have a button component or a modal view component or what have you. If you have a GraphQL API that supports a few basic interfaces required by Relay, you can plug Relay into your React application and allow each component in your React application to specify its local data needs. React knows how to combine the local data needs of all of the components in your UI, compile them into a larger GraphQL query, and issue those queries to the server on your behalf. So your components and your front-end web application, by and large, isn't doing a lot of manually interacting with your back-end API. Additionally, Relay kind of has an object identifier for each object in the UI, and when you mutate a given object, it knows how to update all instances of that object in your UI for you. So it gives GraphQL APIs superpowers. If you're working with GraphQL, I highly recommend looking into it. All right, why do we love GraphQL? It's strongly typed. All of your clients and servers immediately explode if you do anything that is not in line with the type graph for your API. So you also, as an API author, you don't have to implement any sort of type validation. Your frameworks take care of that for you. You do need to implement value validation to make sure that a name has at least 3 characters or what have you, but type checking is handled. Basically, yeah?
Can you define custom types, like, you know, at least 3 letters using like TypeScript will allow you to say a type that is at least 3 letters of like a word?
So GraphQL won't do that for you. It's not part of the GraphQL spec, but you will almost certainly do that when you're building an API. You'll implement some sort of value validation along those lines.
So it is value, not type.
Mm-hmm. All right, so types are always exported from backends to clients. It makes absolutely no sense to manually edit types in your client code. You can run an introspection query on your server, get all the types, and there are tools to translate the GraphQL API server types into the types that are usable by your GraphQL client library. This means that you can integrate these server types into your CI pipelines, and you can fail your CI pipelines if your clients are relying on any fields that have been removed from the API, or if they're querying for data that doesn't really exist. So we get a lot of safety and security here. Clients can ask for exactly the data they need, including data relationships. So basically, it's up to our API framework to figure out which resolvers to execute based on the query that was sent to the server. Clients have a standard way for traversing our graph. And if you build a nice enough GraphQL API, hopefully what we can achieve is we can actually put something along the lines of SQL in the power of our clients. So our clients will be able to build whatever interface they like based on whatever part of our graph makes sense for them. All right, GraphQL provides more functionality than I can cover today. It supports composing larger queries out of smaller query fragments. It supports aliasing fields and a lot more, actually. Tons of, it's got a very rich ecosystem. And basically what we're doing is we're trading HTTP semantics for our typical strongly typed or object-oriented programming semantics. So we get, I think, a lot more of a familiar interface for interacting with our GraphQL APIs than we do interacting with REST APIs. Like all of our standard OO tooling, there's kind of a version of that tooling that applies to GraphQL schemas. And really what we want is to put control in the hands of clients. When we were building REST APIs, we were often over-indexing our APIs to a single client. And what we would get in the scientific space is that we might make one mainline client, our web UI, for example, but we had researchers or other people in the community who wanted to focus on a slightly different set of functionality than what we made first class in our UIs. They may choose to be more interested in data management than in the phylogenetic trees that we were exposing. And since we were really only building our APIs for a single client, they wound up not having some of the functionality they needed to provide another perspective on top of the data that we were exposing. All right, GraphQL is perfect. Ignore the slide. All right, so there are definitely some drawbacks. Since GraphQL is a lot less common than REST, there's going to be a learning curve for both API authors as well as API client authors or users. The queries are a little bit more complex, so users are actually going to have to read the docs to some extent, or at least use a GraphQL Graph Navigator tool or something to figure out how to compose the queries that they need to make. As we said, GraphQL doesn't really integrate very much with HTTP, so depending on what types of HTTP infrastructure you have up and running, caches and so forth may not work as well with GraphQL queries may not work as well with GraphQL as they do with REST. It's easier to DDoS your API. You can write a very small query that does a very lot of work on your API service. So this is something that we need to keep in mind when we're exposing a lot more power to clients. Frameworks usually have a bunch of tools that kind of help limit the bloat here, but when authoring an API, make sure to pay attention. Okay, yeah. There's also, yeah?
Sorry, could you just tell me what DDoS is? Distributed denial of service.
Yes, denial of service. So basically, you make a bunch of cheap calls to a service and make the service do a lot of work, and if you do that enough, you can bring down your service. It runs out of capacity to serve all those requests.
Can you say something about the speed differences between REST? This sounds a bit slower than REST in general.
So speed, performance is subject to a variety of different factors. So requesting one object in a GraphQL API and requesting one object in a REST API, they're going to be relatively similar. Your API frameworks do a little bit more for you in GraphQL, but it's kind of in the noise. But if you're making a query that fetches tons of data, applies lots of filters, you have the potential for one query to be slower than a normal REST API request, where you're typically fetching a lot less data. We've got some tools that help us with the performance here. We can run our different resolvers async, or we can send them off to threads or whatever. We have the full power of our programming language environment. But yeah, you can use profiling tools. It just kind of depends on the implementation of your GraphQL service.
Some sort of trade-off, isn't it? Because, like you say, you might be doing 15 requests to a REST API to get the data you want, as opposed to one or two.
Yeah, there are trade-offs there. In some cases, your clients may know how to issue all of those queries asynchronously and maybe not extend your wall time with REST APIs. But your REST APIs can also do that same thing internally. It can spread out all of those additional queries internally. So something to pay attention to.
Okay, sorry, just to interrupt. We have a request that could the speaker repeat questions from the room? So we've had quite a lot of questions. Sorry, I just noticed that just now. But yes, we can also pass the mic around.
All right, I will repeat questions from now on. There are some criticisms of GraphQL's versioning strategy. Basically, the core GraphQL project basically takes a hard stance on versioning, and that your APIs should not break compatibility. That said, I think that's kind of the same for REST APIs. You can version your REST API endpoints the same way you can version your GraphQL API endpoints. So honestly, I think some of these versioning concerns are a little bit overblown, so I didn't wind up putting a bullet point up for that. Their versioning is overall relatively similar, whether you're using REST or GraphQL. And basically, it's hard and terrible. All right, so CZI wound up in a situation where we were shifting focus a little bit. We were kind of going to be putting some of the projects that we had been working on the back burner, and we needed to stand up some new services to enter some new fields of scientific research. So based on what we'd learned here about GraphQL, we know that we want to build a GraphQL API this time. We don't want to continue hand editing REST API endpoints for the rest of our lives. We typically at CZI store metadata in a relational database service. Postgres is our go-to, but it doesn't really matter. And we know that our schemas are going to evolve, so we're going to have to make sure that whatever we build is going to be able to evolve as our schema evolves. And we're probably going to have to build more than one new API between now and probably even the end of the year, and certainly more next year. So based on this, we know that we need to build a GraphQL API. Oh, thanks. Wow, I'm actually running out of time. All right. There's a ton of work to implement a fully connected graph. So in our little simple schema, if we want to make sure that you can reach every node from every other node, we need to write 7 resolvers for our little tiny 3-table schema. And typically, our schemas have way more than 3 types in them. There's some common patterns here, so we can get a little bit of code reuse when managing all of these different relationships, but still, it's kind of a lot to manage. And as the gentleman in the back mentioned, security is an issue. We take security very seriously at CCI, so we can't just write naive queries to our backend. We need to make sure that you only have access to the data that you are entitled to have access to. We had written some code at CCI where we basically put all of our authorization policy directly into our application code. This turned out to be a pretty bad move in that every time we needed to add a new permission or a new role or whatever, we were updating a whole lot of code. So we decided that we wanted to keep our authorization policies separate, and we would like to have declarative authorization for our new system. So here's just kind of one example of what a declarative authorization policy might look like. We can determine who has access to view or create or update a given resource. All right, so we know that we need to build a GraphQL API. It needs to work with a relational database backend. It needs to have security. So we have kind of 2 main paths forward here. We can create our types as we need them and our additional functionalities as we need them. This gets us up and running really quickly. I don't think it gets us up and running any more slowly than it would be for a REST API of equivalent investment. But this kind of has all the same downsides of we're always playing damage control. Or we can solve this problem in front of us, or we can write a tool to solve the problem right in front of us. It definitely won't annoy everybody who needs a solution right now. So basically, we can build a tool that makes it easier for us to build and maintain these APIs. It has higher upfront costs, and our code base might be a little more complex. But the idea here is that we'll be able to get return on investment as we build more APIs and as our APIs evolve. So we chose Route 2 here. We are not the first organization to run into this problem. There are existing tools, and here's just a small selection of the tools available in the space. They're great. Please use them. Look them up. I've used Hasura personally. It's excellent. Hasura, Supabase, and PostGraphQL all have SaaS offerings. So if you're worried about figuring out how to host a GraphQL API, those options are available. But they weren't going to work well for us. We are a Python shop. None of the previous examples use Python. This isn't a deal killer. We're software engineers. Most of us are polyglot in some way or another. But since we're in the scientific field, Python is pretty heavily favored in scientific communities. It was a concern. Most of these other solutions also use PostgreSQL row-level authorization, which is excellent. It's very powerful, full-featured, but we have some resources that aren't in a relational database, so we were going to need to bring in another authorization solution anyway, and we would like to use a single authorization solution for all of our resources. And the actual deal killer is that we knew that we were going to need like the equivalent of SQL group by functionality sooner rather than later. And so we would have to get really familiar with the ecosystems of one of the tools on the previous slide to figure out how to add this functionality. And kind of all of these items combined led us down the path of we've decided that we're going to build our own tool. All right, so basically we have 2 main ways to build our own tool. We can build a mega framework that basically inhales our schema and then outputs a fully functional GraphQL API. This is totally doable. I have seen tools that do this. However, the code uses a lot of language internals. It's very abstract. It's kind of crunchy, hard to reason about, hard to debug. Or we've got kind of option B, is we can use CodeGen. So we can generate the code that we need. This has some downsides in that it means that we're maintaining a bunch of template code, and our template code is fairly ugly. But the generated code is really direct and integrated with standard Python tooling. It's easy to debug, and it's easy for us to piecemeal test adding new functionality to our generated code before we figure out how to update our CodeGen templates to support this new functionality. So it had a really nice developer lifecycle. So we chose to work with CodeGen. And so we know that we want a CodeGen, a Python-based GraphQL API, and we have a relational database backing it. And we're basically looking to translate GraphQL to SQL. It turns out this is actually pretty achievable. Writing a translation from a GraphQL query to an SQL query is not that bad. There are some libraries that do this for us, and we relied heavily on some previous implementations to build our own. All right, so we need to build this API. We need to define a schema for, like a meta schema for the API that we want to expose. We have SQL, where we can generate our schema as relational database tables. This is fine, except that we want to expose a bunch more functionality via our GraphQL API than SQL can express. We might have type inheritance, we might need field or value validation, and so on. JSON schema is pretty widely adopted in the engineering community, but it focuses heavily on validation and a lot less on defining schemas, so it wasn't a great fit. And the BioPython community has a tool called LinkML that basically gives us a nice, concise YAML spec for how to define a graph schema. We chose to go with GraphQL, and I'm speeding it up. So here's kind of a quick look at what LinkML schema definitions look like. Not all that different than our GraphQL schema definitions earlier. We can define some enums. There's a top-level enum key where we can define multiple enums. There's a top-level classes key where we can define multiple classes. For each field in our class, we have the option of, I don't have any examples here, but we can also apply value validation. So we can say that this integer must be between some value and some other value. We have some templates where we basically throw our schema at all of our templates. And this is some basic Jinja 2. Jinja 2 is the default templating library for Python, so that's just kind of went path of least resistance. We can take our schema, we can throw it at our templates, and we can generate a whole bunch of code really easily. All right, so we take our LinkML schema definition, and we don't just output one file for each type in our schema. We basically need to output ORM code, so this is SQL Alchemy code. We need to output GraphQL API interface code. We need to output authorization policy code. We also output test structures as well, so we get a lot of mileage out of our templates. Under the hood, we're basically trying to use all of the best-of-breed current Python libraries. And this is how everything kind of wires up. You start with a schema definition, we introspect that and apply it to Jinja 2 templates. We output SQL Alchemy code, test fixtures, and we back all that by Strawberry, which is a GraphQL, async GraphQL framework for Python. And then we run Strawberry inside a fast API, which is an async, typically REST API server for Python. There are some functionalities that GraphQL almost can't do, such as returning streaming files, file data, anything that isn't JSON. So it's nice to still have the power of a REST API framework to kind of back some of these functionalities. So what we've built so far, we've got security, we have authorization policies enforced. We can handle authorized file reading and writing with S3's protocol as a backend. There are a lot of implementations of S3's protocol, so this can work with a variety of different actual backend data stores. We got that advanced aggregation with group by built in, and we support filtering based on related fields, any field, and so on. We still have some work to do. Our pagination at the moment is fairly weak, so this is something we're working on. We need to work on making our outputted API code a little bit more extensible via some sort of plugin system, supporting views, and we actually have a variety of work still to do, but we've made a lot of progress. All right, wrapping up. Please use, or next time you need to build a web service API, please at least look into GraphQL. It can provide a lot of functionality. There's a lot of existing code and documentation out there for it. It can be a lot of work, so look into frameworks that kind of help you build GraphQL APIs more easily. And yeah, we built one possible tool. We're looking for people to work with it, give feedback, and so on. All right, questions?
Okay, thank you so much, Jessica. That was a really nice explanation. Yes, so in the spirit of rebellion that we were talking about earlier, we've had a lot of questions already, not through the Canopy app, but there are a few which hopefully we have time for, which I'll go through. Okay. Some of them are quite long, so I'm going to show you them.
Okay.
as well. Okay. So the first question, all examples are using relational databases. How suitable is GraphQL when using document-based, no SQL databases?
So GraphQL is suitable for whatever backend data store you may have. It's just a matter of deciding what interface that you need to expose via your GraphQL API and how you're going to translate those queries into whatever your data store or event store is on the back end. That's really easy with SQL, but you can do the same thing for document-based databases and so on.
Okay, cool. And the next question, can GraphQL avoid having to duplicate the whole server schema in the React front end?
I've always seen that as a feature and not a bug. Basically, your React service imports your API schema. So then you have access to your entire schema that way. It's not that your React application has to manually do anything to handle all of your graphs types.
Okay, the question's changed. Okay, next question. One problem I have with REST is avoiding having to duplicate the schema in server and client. This is partially solved by open API schemas and...
Oh, okay.
Oh. Okay then. Well, I think... Oh, it's disappeared. Okay. There's another question here. Is it possible / convenient, in brackets, sensible, to map between REST and GraphQL schemas?
It is possible. If your REST API has a reasonably standard way of representing relationships in your schema, you can basically put a GraphQL API service that overlays that REST API service. There's a tool called GraphQL Mesh that actually specializes in this. It specializes in aggregating data from a variety of different backend sources, whether they be REST APIs, GraphQL APIs, more, and providing a unified GraphQL schema.
Okay. Okay, and I think that sums up the questions. Thank you again, Jessica. It was really good.